Okay guys, welcome back to the break. This is like my fourth take on this thing because I think I messed it up a few times, but I hope it works now. So yeah, welcome back. We're going to get straight into week 5, and we're going to start with sequential logic. So sequential logic, I think this was taught pretty well in class, but I think the concept wasn't, so I'm just going to go over that in more detail. So any circuit where the current input depends on the current output depends on the past output is a sequential system. And this is very important to understand. It means that you need to know the past state to know the current state. It may or may not depend on present inputs, like we'll talk about that in week 6, but most importantly, it has to depend on the past output. That makes it a sequential circuit. A reminder that combinational circuits are only dependent on present inputs. They are not dependent on the present output is not dependent on any past outputs. So this means that in a sequential circuit, the output itself is linked back as an input, because then it has to influence the new output, which will then influence the new input. Why is this useful? For example, a circuit that can count up needs to know what it's already counted to. So if I told it to count from or like keep counting till you die. Basically, you will start at 0 and then you say 1, 2, 3, 4, 5, and so on. So you'll remember the number you counted to and count up from that, which then makes the number you've already counted to, which then you'll count up from, which then makes the number you've already counted to, and so on and so forth. That's what this is called sequential logic. It causes a sequence of events. However, if you fell into a coma somewhere and you woke up and I told you keep counting, I would be incredibly sadistic, but you wouldn't be able to count. You would tell me, I don't remember. And the simple answer, why would you not remember? Because you literally don't. Computers also need to remember, and that means that to use a previous output, we need what's called memory. Memory is the other half of the computer's power. So one half is processing and the other half is memory, and both these together form the power of a computer. So it's important to understand sequential logic to be able to implement memory. Well, how do I implement memory? Here's the simplest memory circuit. 2 NOT gates. Here I can place a wire, and if the wire is high or low, it will now remember that high or low even after I remove the wire, because that state is going to flow through the circuit. If then I put another wire here and I check what the state is, I can figure out the state. Similarly, if I now put another wire in and I again change this to something else and now remember that, and again I put another wire in check, I can figure it out. This is a very clunky memory module, but it's a good start. So let's get with an actual memory module. Let's start with the SR latch. It's called a latch because it can latch an input to a certain value. That means it remembers an input. Now, something I really want to explain is what's called the idle state of an SR latch, or the idle state of any memory element. For an SR latch, for an SR NOR latch, the idle state is S equal to 0, R equal to 0. That means that you can have an S input across time look something like this. Flat zeros, okay? And during the state, what is Q? Well, the correct answer is we don't know. Q actually depends on a state which has happened in the past. Okay, this is really important to understand. So here Q is equal, so what do I mean by that? I mean that to know the state of Q while S equal to 0 and R equal to 0, we need to know what S was first and what R was first. That is, what was the past state of Q. So when I said S equal to 1 and R remains 0, this is called the set state. Now set is a keyword that is used in all of memories to explain the term setting the memory to 1. So this can store 1 bit of memory, and that 1 bit can either be 1 or 0. So Q is that stored bit. It'll either be 1 or 0. And again, I want to say this is just a single pulse. So for a single moment of time, you just set S equal to 1 and then it keeps staying 0. Now, no matter what time I check this at, I will always get Q equal to 1. So if S equal to 0, R equal to 0, Q will be 1. I know that at some point S was 1. Similarly, if I set R equal to 1 and S remains 0, it resets Q to 0. Now, no matter when I check S and R, no matter when I check S and R, as long as they're in the idle state, I will know the value of S and R before by knowing the value of Q. So why is this important? Let me give you an analogy. Imagine you have a room with two doors, and one door has a sensor S and one door has a sensor R, and you can probably see where I'm going with this. You can only enter through this door and exit through this door. So you enter through this door. Briefly, you walk across sensor S, spiking it. And when you walk across sensor S, well, what you don't know is that S and R are connected with an RS latch to some central CCTV system, and it shows this central CCTV system is constantly reading the value of Q. It sees the value of Q become 1, and now it registers the room as occupied. Similarly, when you walk, now you could be in this room, and you could leave at any time. That would set R back to 0, that would set this screen to vacant. But what's important is the person looking at the screen, the security guard, doesn't need to be there when you walk into this room to see that the room is occupied. The room remembers its state. That is, if they were walked away and they were having their coffee while you walked into the room, you pulsed S for a brief moment. But now, when they walk back, S is 0 and R is 0. Yet they know the room is occupied because you just pulsed S as high and you haven't pulsed R to high yet. So they know the room has to be occupied. Now, what if S equal to 1 and R equal to 1? This is what's called a paradox. Paradox or impossible case, whatever you want to call it. This is a case which you cannot reach and you should not reach. It will cause a lot of contradictions. It will cause Q to be equal to Q complement if you actually do the math, and that doesn't make much sense. So yeah. But what if S equal to, so this is the system for a SR NOR latch. What if your default state of S is actually high? In that case, you want to use an SR NAND latch. This time, spikes are not registered as pulses high, they're registered as pulses low. So at this point, Q became 1, and at this point, Q became 0. And at this point, Q again became 1, and at this point, Q again became 0, and so on. So this is the, and again, there's also the paradox case of S equal to 0, R equal to 0, which is both of them being outside their idle states. So yep, that is how that works. Moving on. So this is the SR with enable. Now this is important. Usually S is not just a random input, it's usually connected to a circuit, something like this or like this, I guess. Yeah, so this could be any circuit, whatever it is irrelevant, but that means that the values of S and R are constantly changing. But what if you only want to store a value of S and R at a particular point? Well, that's when you use what's called an enable. This is a NAND enable, so that means that when this enable is high, the value of S and R are actually read by Q and Q complement, and it actually updates the SR latch. Without an enable, the value of S and R are constantly going straight into Q and Q complement, and in that case you can have unwanted changes to S reflect in Q and Q complement. So an enable allows you to fix that. By when the enable is off, no matter what happens to S and R, these are tied S equal to 1 and R equal to 1 because these are NAND gates, and this is the idle state of a NAND latch. So this will think that nothing is happening to it, and it'll just store its own memory. Only when you need to store something, you turn the enable on. Moving on. If the SR latch was Daniel, then the D latch is the cooler Daniel. The D latch is a kind of special version of the SR latch which removes the double ones of SR by connecting R as D complement and S as D. So if you actually notice, you might realize that this latch does not work without an enable. If you remove this enable, this turns into a switch, kind of, where if I just push D in, if I set D equal to 1, it has Q equal to 1, and if I set D equal to 0, it has Q equal to 0, so it doesn't remember anything. But what I can do is I can put an enable. I push the switch in or I leave the switch out, I turn the enable on, and then I turn the enable off, and now it remembers whatever it was, and I can then do whatever I want to the switch. This D can keep changing and it won't affect the values of Q and Q complement. And again, I can always, just like with the SR latch, I can read values out of here at any time. I just can't store them unless the enable is on. So I'm going to go over two asides very importantly, which will try and help you understand this a bit better. Number one, what is a clock? CLK. What does a clocked circuit mean? What does a sequential circuit mean? What does a synchronous circuit mean? Well, sequential circuits are sequential for a reason. A clock pulse is essentially just a special wave generated which goes high and low and high and low and high and low. This is a square wave. You can make this using an oscilloscope, and using different devices, you can make these waves as well. But here's something interesting. What if I connected this high-low pulse to En? Well, let's look at either of these, EN-SR or EN-D. If I connect it to EN-SR, you will notice that whenever this clock pulse is high, it activates the memory module and allows me to store things. Whenever the clock pulse is lower, it allows me to not store anything. So this acts as a jumpy enable. It is, the gate is enabled for half the time and enabled for not half the time. This is great. This makes the circuit level sensitive. So that means at particular intervals, the circuit the memory is on, and at particular intervals, the memory is off. This is similar to if you are in a play, sometimes the lights go off and you can move around backstage, and you can shuffle around the stage. When the lights come back on, you are in a better position to be acting. Another analogy I like to give is that of a beauty pageant. Imagine that you are a performer at a beauty pageant and you're running and there's a magazine showcasing your best moments. You can have the magazine record a continuous video of your ramp walk from the start to the finish, but it won't be really flattering because it won't highlight all the poses you have done. It will highlight all the pretty much everything else. So that's like having no enable on your SR latch. Oh, sorry, kind of jumping ahead of myself there. That is like having no enable on an SR or no enable on a D. This is kind of pointless. But if you do have an enable, you have this low time to adjust yourself. And this is equivalent to taking that same video, but instead of taking a long video, you take clips, short clips of your performance, which then makes it easier for you to adjust in those downtimes. So that's a great thing. It means that you can change the values of D, you can change the values of S and R while the enable is off, and while the enable is on, you just freeze the values. But there's a problem with that. What if you freeze it at the wrong time? What if you freeze it? What if it's high and then suddenly something changes? Just like as if the video clip is running and the model who's on the pageant trips on the stage. That doesn't look good on camera. What if there was a better way? What if instead of taking a whole clip at a high level, we could just take a clip, instead of taking a clip, we could just take a photo, like so. Snapshots at particular moments. This is called a edge sensitive system. And despite sounding like something out of an R18 movie, it is in fact a very useful system that allows you to simply take snapshots. In fact, snapshots are so effective that in the beauty pageant world, they're the only effective way to showcase somebody's poses. This gives you all of this time to kind of from here and from here to just work on whatever you want, and only on that rising and falling edge does the clock actually tick and does the memory actually activate. Just for a split second, it will remember what the values of S and R were. And it will freeze those in memory until the next clock pulse arrives. Another aside, sequential circuit design. Sequential circuits care about past states, and we need memory elements for these past states. So often we use something called state diagrams to represent all these past states and all of these things. So a state diagram showcases the states of a circuit and the pathways that you need and the conditions you need on those pathways to achieve those pathways. So for example, here I have a system of a lock. When the system is initialized, the door is locked. And I can think of if I have 5 flip-flops, A0 or 5 latches, whatever, A1, A2, A3, A4, which are 0 if a digit is correct, and the first digit is correct, the second digit is correct, and 1 if the first digit is correct, and 0 if it is incorrect. So they all start at 0. Then the machine, when it reads all these states, it knows it's in the state 1. When I get one of the digits correct, it jumps to state 2, and then to state 3, and then 4, and then so on and so on and so on. If I get a digit wrong, then it goes straight to the lock state. Makes sense. And then it automatically jumps back to the initialized state where it resets everything to 0. However, if I get all of them correct, it jumps to success. The success state, which then unlocks the door itself using something mechanical. Importantly, a bit of notation. For an output Q, the present state is always Q of t, and the next state is always Q of t plus 1. Think of this as t as the current time and t plus 1 as time and 1 clock cycle. So this is important because sometimes we use notation to refer to the next state, as used often in sequential circuits which depend on past outputs. You will use notation. So this is the notation that we use. Now, talking about edge sensitivity, we have flip-flops. a circuit that acts like that snapshot that only depends on rising and falling edges. The simplest circuit is a D flip-flop. It is like a D latch, but it only works, it's not working on high levels, it works only on these edges. It can either be rising or falling edge or both, whatever you like. And it gives you all the time in between those levels to adjust yourself and adjust the memory values, adjust the value of D. So that clock, whenever it's rising or whenever it's falling or both, will allow D to change. And this gives you Q and Q complement just like in a D flip-flop. Then we have the T flip-flop, which is a toggle flip-flop. It's a variation of the D flip-flop where the value of Q in the D flip-flop is just whatever D was at the snapshot moment. The value of Q in a T flip-flop is dependent on the previous value of Q. So as you can see, this wires back into the input. The value of Q is, if T is 0, is still Q, and if T is on at the snapshot period, it toggles the value of Q, so it flips the value of Q. And then there's a K flip-flop. It is like an SR flip-flop, like a SR latch, but a bit more complicated, and we'll get to why this is useful in a bit. It fixes one of the shortcomings of the SR latch. But all these can be implemented with a D flip-flop, as you can see. So let's look at this. These are characteristic tables of the different flip-flops, and these are very important to understand. These will be given to you on the paper, so you don't need to memorize these, but it's important to understand how they work. So let's look at the D flip-flop. This tells you what Q of T plus 1 will be for any value of D. So if D is 0, Q of T plus 1 is 0. If D is 1, Q of T plus 1 is 1. This is important. It means that you can figure out what your output is going to be based on the current state of D. Over here, the T flip-flop actually has the same thing, but it relies on the present state as well. So if Q of T was 0, Q of T plus 1 will remain 0 as long as T is 0. And if Q of T was 1, Q of T plus 1 will become 1 if T was 1. On the other hand, we have the JK flip-flop. This is a special flip-flop which allows you to overcome the shortcoming of SR flip-flop while still having two inputs. So when you have J equal to 0, K equal to 0, this is the memory state, no change. And when you have J equal to 0, K equal to 1, you have the reset state. When you have J equal to 1, K equal to 0, you have the set state. And when you have J equal to 1, K equal to 1, it's not a failure anymore, it's a complement state. So if you use a bit of thinking, you might realize that if you connect J and K together, if you wire these together, you can create a T flip-flop because the 0 state will be no change and the 1 state will be complement. So yeah. Using characteristic tables, we can actually design what's called excitation tables. Excitation tables are a different style of table where the inputs are Q of T plus 1 and Q of T, and the outputs are what. Now the output, not as the output of the circuit, but the output of the table, the one in the rightmost row, is the values that must go to achieve this Q of T plus 1. So I write down all combinations of Q of T plus 1 as I would in a truth table, and I figure out what values of D do I need to get these Q of T plus 1s. So for 0 to become 0, I must keep D 0. For 0 to become 1, I must keep D to be 1. For 1 to become 0, I must keep D to be 0. For 1 to become 1, I must keep D equal to 1. Oh, this is for a D flip-flop, as you can see. The next step is swap the inputs of the truth table and the outputs of the truth table to get this. And now you can use a K-map. Make Q of T plus 1 the output, make a K-map, and draw out your Q and D. However, this is much easier done by just looking at the truth table. As you notice, Q of T plus 1 is 1 wherever D is 1 and 0 wherever D is 0. So Q of T plus 1 is just T. What if one of the values is a don't care? Well, there is in SR inputs, one of them is not only there's a case for the inputs being a don't care and the outputs being a don't care. The inputs being a don't care, that shouldn't be possible. Well, let's get to that. So let's look at the obvious ones first. To set a 0 to a 1 in an SR flip-flop, there's only one way to do it. It is set S equal to 1, set R equal to 0. Similarly, to set a 1 to 0, to reset a 1 to 0, you set this to be 0 and this becomes 1. However, to go from 0 to 0, there's actually two ways if you think about it. First of all, there's the idle state. 0, 0. S0, R0. But there's also the reset state, which sets anything to 0. So this could be 0, 1. That means that now R is a don't care and S is always 0. So you're forcing 0 to either be set to 0 or just keep 0 to stay 0. And same goes for the logic to go 1 to 1. So now S becomes the don't care. How do you reflect this? Well, when you swap the values in the table, you will now get this table. Okay, I hope I copied that right. Yeah, I think I did. And then q complement become, sorry, q of t plus 1 becomes 0, 1, 0, 1. And over here, well, where is q of t plus 1, 1? Here it is for s equal to 1, r equal to 0, q equal to 0. So this cell gets filled in over here. And for q equal to, and also another one over here is for q equal to 1, s equal to x. So it could be 0 and or 1, and r is 0. So then you have to fill in two cells, 1, 0, 0 and 1, 1, 0. But here's something interesting. We know that for an SR latch, 1, 1 is forbidden, not allowed. That means that we don't care what happens at 1, 1. So we put down two x's. So now not only does the output have don't cares, the input doesn't have don't cares as well. So input don't cares are reflected by a double entry on the truth table, output don't cares are still reflected by an x. Now I can make my groups, this group and this group. And I'm going to erase that truth table up there real quick. And as I mentioned, the groups will be this group over here, this group over here. And once we get these groups, well, we can then figure out that q of t plus 1 is s plus r complement q with a special condition sr equal to 0. So this is an equation where sr is 0. And all these equations you see for q of t plus 1 are all what's called characteristic equations. And now for something a bit tougher, jk flip-flop. This is a table given in the textbook or in the slides for jk flip-flop. This is a bad table. Don't use this table. The reason is what they've done is violated their own rule of making q and q plus the inputs and making jk the outputs and then inverting it. Instead, they've made q and j and k the inputs and then made q of t plus 1. This is kind of pointless. You can actually achieve the same effect by just using the proper table, using the proper don't cares, and I will explain that here. There you go. This is the same table. As you can see, you can have q plus become 0 by either staying it at 0, so 0, 0 being the memory state, or 0, 1, that is the reset state. So k equal to 1, that means k becomes a don't care. Similarly, you can have 0, 1 become 1 by either setting it to 1, so 1, 0, or complementing it to 1, 1, 1. Same effect, but now k becomes a don't care. And this goes for the other two as well, which then gives us the equation jq complement plus k complement q. Lovely. So this is all of the characteristic equations. These will be given again on the sheet. You don't need to memorize these, but please understand how to use them. In an analysis, you will use these to draw them out. So if you see a bunch of things feeding in, like, gates, circuits, AND gates, OR gates, NOT gates, all of them feeding into D, and then D going into a flip-flop, you should know what the output will be. The output will just be D. Whatever D was before all this, when you evaluated it, it'll still be Q of T plus 1 as the output. And the same goes for all these. So that's how you do analysis questions. That completes week 5. Moving on to week 6, Mealy and Moore models. So a quick recap. In a combinational circuit, the future output only depends on present input. In a sequential circuit, the future output definitely depends on present output and may or may not depend directly on inputs. What do I mean by directly on inputs? Well, if I have a memory module and I have inputs X and Y into it, and then I pull out in something here, I have a circuit and it goes to the output. The output here depends on the memory module. That is, only when the memory module's output updates does this output update. So if I change X and Y halfway through a clock cycle, it won't change the output instantly. I have to wait for the clock to rise or fall, or both, and then that'll change the output. However, this case that we have here is called a Moore model, first off. And as I mentioned, any changes will first affect clocked memory element, which will then affect the output. Outputs cannot change outside of the clock configuration. However, if I have an input Z that is directly connected to the output, then any changes to X and Y definitely won't reflect instantly in the output, but any changes to Z will reflect instantly in the output. This can cause inputs that change out of clock can cause outputs to change out of clock as well. This is called a Mealy model, which means that Q of T plus 1 is a function of Q of T and the inputs directly. So yeah. And that concludes everything. A few tips: make sure you review the labs, as I think they're the best resource for this course. Try to do as much homework as you can, and don't stress out too much about it. If you did enjoy this, if it did help you, just drop me a thanks on my Discord and say you enjoyed it, or just drop a few dollars on my Ko-fi. The link is early on in the slides and in the description. Anyways, have a good one and good luck on the examination.